who's going to be talking about optimization of a time temperature indicator system for real-time monitoring the quality of Australian red meat. So all the way from dairy to microbiology of red meat. So thanks very much, Chongyue. Take it away when you're ready.
Yeah, good. Good afternoon, everyone. Thank you for coming to my presentation today. My name is Chongyue, and this is about my project, Optimization of the TTI system for real-time monitoring the quality of Australian red meat. And my presentation will be divided into about 7 parts. In the beginning, I will provide some background information for you guys to understand the purpose of my project. Then I will list some research questions I want to address in this project. The experimental method will be generally introduced, and I will discuss the results after each part of the experimental method. Next, I will give an overall conclusion about the key findings of my project and give some further research recommendations for this research area. First, you maybe all know Australia is one of the world's largest red meat exporter. It undertakes a lot of international trades, and nearly 70% of them was with the distant countries, including Middle East, China, Korea, and so on. It gained good reputation by producing high quality meat with long shelf life, which relies on the good supply chain management. However, recently, due to the trend of globalization with increasing competition, Australian red meat industry is facing challenges to be more competitive and satisfy the consumers' demand. Existing supply chain management need some improvement to be more competitive. Because currently temperature data logger combined with the predictive microbiology are generally combined to predict the shelf life of food product. However, these tools either have low efficiency or require the professional knowledge for the operator. Therefore, some changes are required. Then the concept of temperature indicator system was born at the right moment. It is a tool that provides a real-time monitor about the food product's shelf life. It can be classified into many types based on their mechanism, such as physical, chemical, and microbial TTI. In this project, I will only focus on the macro TTI system. This is a simple explanation about the microbial TTI system. It's mainly composed by 3 parts. The specific microbes as a candidate, and the growth medium for the microbial growth, and the pH indicator. The mechanism of this microbial TTI is that the microbial candidate grow in the growth media, produce byproducts to acidify the medium, and the pH indicator causes color change of the medium because of the pH reduction. If a significant color change of this TTI is observed at the end of product shelf life, we can consider it as a success one. The picture on the right-hand side is an example of the commercially microbial TTI, and this product is designed for ready-to-eat food and color change from the green to purple has a good indication. This is a TTI prototype developed by one of the previous students, and it's designed for the Australia vacuum packed red meat. This prototype used the Canobacterium as a microbial candidate and used the BHI medium with 1% added glucose as a TTI medium and 0.01% chlorophenol red as the pH indicator. This picture on the right-hand side shows the color scale of this TTI. It's the change of pH indicator with the pH. This is what the student had done before. He used the Utah's shelf life model to predict the shelf life of vacuum packed meat and evaluated the performance of this TTI at 15 degrees. But this TTI's performance was not good because the color change is not obvious at the end of the shelf life. From this graph, we can conclude some key findings. First is the two strains, Canobacterium strain 1 and strain 18, do not have any significant difference. In my research, I only use one of them to reduce my workload. Next is the Canobacterium growth is much slower than the predicted growth rate of meat microbes. In the Canobacterium's growth curve, we can find two phases with very slow growth rate. First one is at the beginning. We call it the initial lag phase. It is the microbes try to adapt to the new environment. So it's very common in microbiology. And the second one is at the middle part of the growth. And we call it the secondary lag phase. This phase is suspected to because the primary carbon source is used up. From this information above, we know we need some optimization for this TTI to be more successful. Then we begin to consider some possible ways to optimize this TTI. We know this TTI is false because the color change is not obvious. So we may find many ways to accelerate the pH reduction. At least some possible ways in this page. Based on the information we already have, I decided to test the increasing glucose level and manipulating the initial Canobacterium level. If these optimizations are successful, I will test the TTI's performance under a refrigerated temperature. It is 2 degrees and 4 degrees in my project. Following is about my experimental method. First is about evaluating the effect of glucose on TTI at 8 degrees. I choose the 0% glucose as a negative control to compare with the 1%, 5%, and 10%. To make the results look clearer, I divided the variable counts and the pH into two graphs. The graph on the left-hand side shows the Canobacterium growth curve in TTI with different glucose levels. And the right-hand side is about the pH change over time in the TTI system. The red, blue, black, and green samples reference the different treatment groups with 0%, 1%, 5%, and 10%. From these two graphs, we can find that the glucose didn't have any effects on the secondary lag phase because all of the treatment groups, the secondary lag phase were not observed. And we can also find the high levels of glucose, which is 5% and 10% glucose, have a significant inhibitory effect on the bacterial growth rate. Even the pH reduction of the higher glucose concentration groups is slower than the 1% glucose one. Because the pH reduction will stop if there is no supplementary glucose. We can look at there. It just stop at about 6.2, and it's not enough color change. So we just choose 1% supplementary glucose in our TTI. Next is about the method of how we evaluate the TTI system with different initial level of cyanobacterium. In this experiment, I choose 3, 4, and 5 log initial level to add in the TTI medium. This is the result of this growth study. In this graph, the yellow, red, and blue symbols represent the growth curve of 3 log, 4 log, and 5 log cyanobacterium. We found the growth rates are not significantly different between the different initial level, but the pH reduction are significantly different. Before we interrupt this result, we should know something about the concept of Utah's shelf life model. It is based on predictive macrobiology, and we can use it to predict a food product's shelf life based on its storage temperature and the initial total viral counts of the meat of this product. Through multiple comparisons between the experimental data and the predicted shelf life, we can conclude that the TTI system contains 3 log higher cyanobacterium than the initial TVC on meat, showed a good correlation with the predicted shelf life of VP lamb. Yeah, I just call it a VP. It should be vacuum packed meat. So this is the results. We can just see the pH reduction here, and these 3 compare with the predicted shelf life there. If at this time the pH, the color change of this TTI is significant visible, we can just say it's from purple to yellow, purple to yellow, purple to yellow. So we can see the performance is good for this TTI. But in the context of Australia red meat, we know the initial microbial level of meat is approximate 2 log. So we just choose a 5 log cyanobacterium initial level in TTI to optimize this TTI system. In this part, we test the performance of this optimized TTI at both 2 degree and 4 degree. Because the experiment of 2 degree is still ongoing, so I will just show the 4 degree results here. This is a graph and a conclusion in the table. Just like the previous part, we can conclude that this TTI system could be used to accurately indicate the shelf life of the vacuum-packed lamp at 4 degrees. So in this part, I will give an overall conclusion of my key findings. First, we found glucose didn't improve the performance of the TTI system. Thus, we still choose the 1% glucose in our TTI. Next, we found the performance of TTI system can be improved by just simply manipulating the initial level of cyanobacterium. In this case, TTI system with 4 log initial cyanobacterium could be used to accurately indicate the quality of Australian vacuum-packed lamp at both 4 degrees and 8 degrees. There are some of my research recommendations for the further experiment. First is about the because now our experiment is under a constant temperature, so a dynamic temperature is encouraged to validate the accuracy of this TTI. And now this TTI system is still conceptual. Further development are required for its commercial use. And after we finish the dynamic temperature experiment, maybe a shelf life study should be conducted for the vacuum packed lamp to further assess the accuracy and the practicability. Because the Utah shelf life model provides both vacuum packed lamp and beef shelf life prediction, so maybe a further optimization for this TTI can be conducted to design for the VP beef. These are some references I used in my presentation, and that's all. Thank you.
Okay, thanks very much, Chongyue. Does anyone have any questions so far for Chongyue on his presentation, please?
I've got a question, I guess, Chongyue. So do you know what will happen with your research now? Is there plans to take that forward?
Sorry, could you repeat the question again?
So obviously, very soon you're going to hand in your thesis and your research will be finished. Do you know if there are any plans for anybody to use this research to apply that to, real life?
Yeah, I was thinking about the designation of this TTI previously. Maybe just designed as a small smarter label on the red meat packaging. It can contains with 2 components. Which one? The first one is about the we can mix the bacteria such just the cyanobacterium as the bacterial powder and put it in the maybe something like a vacuum. And the second one is about the medium we designed for the cyanobacterium growth, and it can be stored at room temperature. And if we want to use it, we can just mix the components with the bacteria and stick it on the package. Then it will indicate the shelf life of the product.
I think so. I guess I'm asking whether anybody is going to do that. So are there any, so these are things that you can do in theory, but are there any plans for somebody to actually do that? I guess that's what I'm really asking.
Yes.
Awesome.
Is there any explanations for the secondary lag first?
So I'll just read that out, Chongyue. So a question from John. Is there another explanation for the secondary lag phase?
Yeah.
Could it be due to bacterial interactions during growth competition? And what does growth of cyanobacterium look like on irradiated meat? thinking about perhaps Laura Rood's experiments.
Yes. About the secondary lag phase, we found it is very significant in the graph of the previous students' research. But in my experiment, when I did the growth study for the Canobacterium, I just can't find any of the treatment exist the lag phase, the secondary lag phase. So for now, the mechanism for this secondary lag phase is not clear, and John said the girls on Canobacterium look like on the irradiant meat. But currently I haven't looked at Laura's findings, so maybe I can't explain this for you. So yeah. Thank you.
Great question, John. Anyone else with a question for Chongyue? No, maybe in that case, thanks very much. Well done. And we'll have the next speaker, please.
Yeah.